Common sense is a big trap when it comes to physics. For example here, if we assume we have two spacecraft traveling in opposite directions at the speed of light, would the speed of a spacecraft relative to the other one be twice the speed of light? By common sense, you might just add up the velocities. However, this is not the case. Here is a more detailed diagram of our situation. I've added in an observer so that we can relate the spacecraft to a stationary point. Each spacecraft has its own atomic clocks, so it can measure the time relative to itself. The speeds have been added in. The observer speed is 0 and uses normal clocks, and the relative distances here as well, spacecraft 1 and 2. The important thing to note here is that if you're in spacecraft 1 and you want to calculate some value from spacecraft 2, you must only, in relativistic work, you must only use what measurement is available to you and what you might know about spacecraft 2, and then multiply it by some factor, which will soon work out. Another entity to add in is the distance between the two spacecraft, which is measured as a velocity u times by either the time from spacecraft 1 or spacecraft 2, depends on which one is measuring the distance. Here we take in this direction to be positive and this to be negative with respect to origin 0 as an x-coordinate basically. If we're in spacecraft 1 and we want to know the position of spacecraft 2, we take our own position and we add the distance measuring the time, our time, and we need to find out what u is at the end basically. And that makes sense here. Same here, if we're in spacecraft 2 and want to find out the position of spacecraft 1, we take away our position from the distance measured with our time. Now, these are factors added in because we don't really trust our measuring system on our spacecraft. Because in relativity, what we learn is that at very high speeds, close to the speed of light even, time slows down for the object, it shrinks and it gains mass. And this is a factor which we'll calculate to see what the factor is when they're traveling at the speed of light. Very simple substitution here. The distance can also be modeled by the speed which each spacecraft knows, the speed of light, and the time on its ship using the atomic clocks, as we said. So we substitute these into these equations here, and I've begun using small letter t because that's the proper way to do it, you know. We're going to multiply these two together, and from that we could find out the y factor for speed of light. Something like this. It's basic quadratic expansion. And now there's two things we can do. We can cross out these, they add the same thing, and from the remaining we can simplify both time 1 and time 2 on the spacecraft to get the following. Then we rearrange right away actually to get this. Let me explain what I did here. For an easier visualization, I took the reciprocal, which simplifies to give this. Then taking the reciprocal back and square rooting, we'll get the factor here. You'll later find that this factor works for all speeds, not just the speed of light, but requires further explanation. And here we're only concerned about this interesting situation. From here, our assumptions are true, that this factor depends only on the speed between the two things we're measuring. Be included in every gamma factor as such, which is basically this speed. What we actually assumed here is that these two are equal, and they are because they're both traveling the speed of light. And since we actually were supposed to assume, which I forgot to tell you, that we assume that these are based solely on the speed of the spacecraft. If the speed of the spacecraft is c in both cases, then they must be equal. And because of that, we prove that it only depends on the speed anyway. Now, if we were the observer and we're watching spacecraft 1, which is traveling at the speed of light here, then the position of the spacecraft would be our position, take away the speed of the spacecraft, but we're using our measurements of time, so this is not supposed to be there, our measurement of time. Same here, if we're spacecraft and we're trying to find the position of the origin, also seeing it travel by the speed of light. The reason why this works is because we may not trust the time systems we use to measure over distance, but because both spacecraft are traveling at the speed of light, which is the limiting speed, is something we can trust, because in any frame rate, anywhere, going anywhere at the speed of light, we don't need to actually dilate the speed of light, because the maximum speed. Replace this by CT1, which is just like we did here, by distance, using the speeds only and the time, is equal to relative, it's just minus t by c. And when we find out, well, since this is negative, but we're looking just for the absolute value, so we don't care if it's negative, we're looking at the speed. So basically, the time as measured on a spacecraft is our time times the factor here. We get our first equations on time dilation, which is the apparent time, which is the time the spacecraft experiences, over the factor, is equal to the time as seen by an observer. Same holds if you replace here this with S1 and this equation up here. Actually, we get S1 is equal to minus S O, because this gives, from the observer's viewpoint, the speed of light times the time of the observer, so it means the distance as we see it from the viewpoint. This gives time experienced by the spacecraft divided by the factor for speed of light to the time as seen by the observer, because we only care about the absolute value. There's no direction here at the moment. Come back to these later. We're now going to prove our initial statement if we're in spacecraft 1. If I'm in spacecraft 1 and I'm looking back at spacecraft 2 to check their velocity relative to me. I'm in my spacecraft and I know three things. Using my equipment only, I know the position of 2 here. Yeah. I know my position and I know the time. Those are the only three things we need to work out UTU. Here's the formula for U, because this takes a negative value, and taking away S2 from S1 will give us the distance, basically, as far as we know in our spacecraft, divided by the time here, will give us our relative view of U. So basically the velocity we see between the two spacecraft, in our spacecraft. And this works because, in relativity especially, because we only used all of our systems of measurement, plus the gamma factor here. Factor is only used when you're transferring your systems of measurement into another frame rate, and the gamma factor speed depends on the speed between those two frame rates. If they're the same speed, it's the same frame rate, no need for gamma factor. To get this, I took out the speeds from the gamma factor to make it more simple. By multiplying T1 to both sides and taking away this from both sides, we'll get this. This here can be factorized like this, and then dividing both sides by this, we get this here. Notice that this value here is equivalent to this value, so after a bit of simple algebra we get this statement, velocity here, and it's actually negative. Sorry, I thought this was distance. It's negative because we're traveling in the negative x coordinate. And what this shows is that the whole speed of expansion, both directions, is simply equal to the observer's speed, which is c. So even though you may think that the spacecraft travels twice the speed of light, it limits off at c. And when we did the same thing with the observer, it also limits at c. So we'll get here a case where it doesn't matter what I look at. If I'm traveling at the speed of light, everything moves at the speed of light as I see it.